The special thing about the third example is that we have a continuous variable and the outcome is infinite. It's infinity here. Here, what we are going to do is to draw a random number x from range 0 and 1. And I have two numbers, a and b, fixed numbers, and I want to calculate the number, the x falls between a and b. Okay, so basically this range here, and I'm interested in your x falling in this range. If I randomly draw x from 0 to 1. And in this case, your number of points is infinite, so your sample space here, the sample omega is any number x such that x is between 0 and 1, right? You cannot count how many x are there because it's infinite. The number of events I'm interested in is your x subset of omega, which is x between a and b. Okay, in this case, your number of elements in sample space and the events are infinite. You cannot do the sample division as we did, just like a flip a coin. In this case, how can we assign a probability? You know, one special thing about axiomatic approach is that we can assign probability as we see fit, as it makes sense. In this case here, I think it makes sense we assign probability as proportional to the length. So your total probability is the length from 0 to 1, and then your probability A is length. How long is your length A and B? So B minus A divided by total length 1 minus 0 is B and A. See, that is kind of makes sense. And if we do this approach, we say, okay, so what is your total probability? Then your total probability, your sample space equals just 1 minus 0 divided by 1 minus 0 is 1. So your total probability is 1. And if you have partition here, suppose I have C here. Okay, so if I want to calculate probability that x between A and C, and I can partition this into two parts, right? Each x is A, B plus x is between B and C, right? And each part is just, see this part, B minus A divided 1 plus C minus B divided 1 is C minus A. See, you can see the total formula still holds. And anyway, we satisfy the three conditions of the probability. And so the key about this point is that we have to assign the probability measure that makes sense in this case. The second question says, what's the probability that x equals a? Okay, in this case, your probability x equals a is 0 because there's no length in one single point. Some people might say, how come? It can be 0 here. Think of it this way: you have infinite number of points in this continuous range from 0 to 1. If you have some positive probability for any single value, then you have infinite number of other points going to get some positive value. Your total probability is going to be infinite. That's not good. So that's why in a continuous range, the probability for a single value is 0. And next, I want to show you, kind of quickly show you the simulation I did for this case, just to drive point home, and you know that our conceptual understanding is correct. And I'm going to open this spreadsheet again here. My spreadsheet, third spreadsheet, random draw numbers here. So in this spreadsheet, I have see number simulation here. What I did is generate random number between 0 and 1. This time rand. The difference between rand and rand between, the rand produce a continuous number, you know, like a fractional number between 0 and 1, and the rand between really generates a, you know, 0 and 1 produce two discrete numbers. So this is generate a fractional number, and my A is 0.2, my B is 0.5, and so I say, okay, so this is just condition here. If my number falls into A and B, I get 1. Otherwise, if it falls out of range, the column D is 0. So I can calculate how many from here, simulation of 21 simulations here. Out of 21, simulation 7 fall into the range. So your total probability is 0.33. Your theoretical probability is 0.5 minus 0.2 is 0.3. So you can see that roughly, your simulation matches our conceptual calculation.